this little asphalt reclaimer tool that has carbide sintered diamond on the tip. And I didn't tell you why this never went into commercial production. Too expensive. It's got 10 times the life, but it's still too expensive. Okay? So far as that goes. Anyway, I just want to mention that. And the brake, Adrian asked about, well, what's the liability for some of these screw-ups? Okay, well, it's sort of like, can you allow a big bank to fail? Okay, if you think of the financial stuff. If it's some lower level person, you're gonna send them to jail, or you're gonna bankrupt them or whatever. But if it's a really big failure, then usually you come to some accommodation. Okay. And to give you an example, a specific example from the aviation industry, back in the 1970s, you have to quench and temper your high-strength aluminum alloys. Okay, it's not the same martensite and stuff. And when we go through aluminum welding, we'll talk a little bit about heat-treated aluminum alloys, which are quenched and tempered, but for different metallurgical result. You get higher strength, but you get different. You don't get martensite, okay, to give you the strength. You get precipitation harder. But in any case, there's one plant in the United States, the Davenport, Iowa works of Alcoa, that has the world's largest rolling mill, and that's where they roll all the plate, 4 or 5 inch thick, 6 inch plate, huge plate in this huge mill for the aircraft wings for Boeing and a number of other companies, okay? So if you're gonna build a huge aircraft, you're gonna have to buy from Alcoa at this plant. And in order to quench these big aluminum plates, they have a series of water jets, and the hot plate just goes under this shower of all these water jets, and it gets quenched, and then later it's tempered. Well, it turns out they discovered a little bit later than they would have liked to, that one of the water jets was plugged in this row of water jets, okay? And it was late enough that Boeing had already done all the machining, put them on aircraft that were flying around the world. And so you had big wide plate, and you had some stripe that never got quenched and tempered. It's just a local defect, okay? Well, at this point, they had to notify the government. The government got one of their Department of Commerce lab, NIST, which is an excellent lab, in Gaithersburg, Maryland. The guy who headed NIST at the time was the guy who didn't get tenure here at MIT before they hired me, okay, Bob Moravian. He's now chairman of Allegheny Teledyne Industries. But he was head of the NIST lab, and they had a partnership here, okay, between the government and Alcoa and all the airlines, and someone was going to have to solve the problem. Okay? When it's a really big problem, there are people who actually want to know about how to solve it first, and then they'll worry about how they divvy up the liability and the cost. Okay? So it turns out they ended up developing jointly a electrical resistance measuring device, a non-destructive probe that you could just put on the surface. I actually have one that costs about $5,000, and you just put it on the surface of the aluminum. You measure the electrical resistivity of the aluminum, and you can tell what the heat treatment is, okay, for certain alloys. And so that was developed under that program, so they could go and they could check the wings at lots of locations to see if they had a bad piece of plate. Okay, I don't know. I wasn't really involved in it. I was too young as a faculty member at the time. Another example I heard was the Citibank Tower in New York City. After they built the tower, they discovered that some of the welded joints were not good enough for seismic loading. Basically, you had a reasonably foreseeable earthquake, and this building was going to collapse. And so when they structural engineers, there's actually I used to have a copy of an article. There was an article in the New Yorker about this whole thing, okay, but it didn't really tell the story that I heard from another point of view. And so you had all the the architects, the engineers who designed the building, you had the contractor who had built it, and a bunch of subs, and then you had the owner, Citicorp. And what were they gonna do? And the story I heard was that John Reed was a graduate of Sloan School. He became chairman of Citicorp when he was 40 years old. Okay? When he was 75, he was chairman of the MIT Corporation. Okay? This guy was a real high flyer. I actually checked with him last winter because his brother had a welding problem. His brother is 85 years old and owns a steel tank welding business down in Tampa, Florida. Not a small one. And they're going to weld this 9% nickel steel. And John Reed found out that there was someone at MIT who knew something about welding. I didn't tell him who that was, but his brother, he said, I want you, he wanted his brother to hire me. And I talked to one of their engineers, and the guy didn't want any help. So anyway, but so I talked to John, and he apologized profusely for his brother not following up on, because he had passed the name on, and I didn't care. I didn't need the problem. But I said, John, can you confirm this story? And the story that I heard, which John didn't completely confirm, he said he didn't remember a lot of it. He's 80 years old now. He remembered the problem, and he remembered everybody getting together and working it out cooperatively, okay, because it was a huge problem. But the way I heard the story when I was in the Sloan program was that they got them all together, and after John Reed and the other people heard how big this problem was, he says, okay, I will pay for it. Citicorp would pay for the repair. And we're not going to get any attorneys involved, but you're going to work at cost, and you're going to work at cost, and you're going to work at cost, and I will pay for all the materials and stuff. And they fixed it, okay? And he remembers that he made some decision in the meeting, but he doesn't even remember about the cost. Because to him, he was dealing with hundreds of billions of dollars, and who cares about, $100 million or whatever it's going to cost to fix it. When the problems are really big, you can often subvert, go around the attorneys, okay? But when the problems are smaller than just $50 or $100 million problem, well, the attorney's going to take control. And then you can't get the engineers together because no one wants to allow their engineers to talk to the others. And it's really pretty dysfunctional, okay? So far as solving the problem. Because everybody's trying to CYA because of who's going to pay for it. When the Seawolf submarine had its $2 billion problem with the wells, well, they worked it out, okay? Because what are you going to do? You're going to bankrupt your only one of two submarine building facilities? I mean, you can't do it. Okay, I remember working for Bell Helicopter on some things, and they had a problem with some, I don't remember, it was forgings or whatever it was, from their supplier. And I remember the chief counsel said, we've got to quit thinking that we can sue our suppliers, okay? Because the suppliers would just say, they could say, we're not going to supply you anymore. We don't want the liability, okay? So there's lots of business decisions that go into things. The problem is when the trial attorneys get in there, they're just sharks, okay? Looking to make a big fee. Which is actually okay, because they hire me, and that's how my kids do college, and they're all through college now, but I got grandkids, Anyway. So, but does that kind of answer your question on liability? If it's really, really big, multi-billion dollars, you usually find some way to fix it. I've got a problem right now, I won't tell you the product, but it's hundreds of millions of dollars of steel fabrication, and they found that they've got a design defect, and we've tried to tell the fabricator that they were supposed to design it, they have a design defect, and these things are breaking, and if they do break at the wrong time, you might kill a few cows, but you won't kill people, but people will be without electricity over a large area of the country, and it'll become a big political problem with the regulators and things like that. Did you know you had this problem? Blah, blah, blah. And it's not just this one area of the country that I'm working for somebody, it turns out as we've gotten into it, they got this problem in other parts of the country. Surprise, surprise, it's the same problem. And I would say, well, when are you going to go find out from the other companies in other parts of the country that are using this product? Well, none of them really want to talk to each other because the attorneys are all afraid of who goes after the manufacturer first and puts them in receivership, but they get their money out. Everybody wants to be first at the trough to get their money out before the company goes bankrupt. Now, in fact, I sat in a meeting with the CEO of one of these companies, and nobody wants to put this company in receivership, because if you want to be in business, you got to buy this product, okay? So ultimately, you get down to usually, if it's a big problem, usually cooler heads will prevail, and people don't want to put their suppliers out of business. Does that answer your question?
Yeah, I was just curious about the dynamics, whether reputation matters more, or the legal framework, whether there might be criminal, like if you give the wrong supplies, knowing that could stuff like that, or just trying to get a sense of the industry in terms of, so that is helpful actually.
Yeah, I mean, there's all kinds of variations of this. The famous one is when Johnson & Johnson found out that someone was spiking their Tylenol, putting poison in their Tylenol, and this was on drugstore shelves. They recalled all the Tylenol. They hadn't done anything wrong, but it was their product and their reputation. If you read the credo, they call it the credo with Johnson & Johnson, that basically sort of comes out of the Hippocratic Oath that they will not do any harm, and they will do what's right. And a number of companies have that and follow that. And Johnson & Johnson got more, there were actually articles that their business improved by more than the cost of recalling all that Tylenol, okay? And they got great press, okay, about doing the right thing, even though it wasn't their fault. By the same token, I was involved in the Northeast extension for Amtrak a few years ago, and they had a British firm doing this $300 million Amtrak contract. Remember, Amtrak's a subsidiary, basically, or it's basically covered by the federal government. So this British firm makes all kinds of commuter train tracks and stuff, electrified train tracks, was in charge of this, and it was a fixed cost contract. And they needed $5 million. Well, they needed a bunch of copper wire for the overhead conductor that these electric trains, run on. If you go out, if you ride it, you look up, you'll see the conductor. Well, I got a call on like the 20th of December one year. Could you go out? The British company was going to buy product from this copper wire, very special type of copper wire, from a little company in Rome, New York. Okay, Rome, New York's influence. And could I go out there and see if this was, it wasn't meeting spec, and could they give a waiver of this particular spec? And, oh, by the way, we have to have a decision before Christmas. This was on the 20th, okay, of December. Well, I go out there and I look at things, and by the 22nd or 23rd, I say, no, can't accept it. Well, at that point, Amtrak issues the order, don't install any of this product, go find another supplier. And the British company said, there is no other supplier, we've searched the world. We can't find anyone who can make this product. And if you don't let us put it up, you're not going to be able to build your Northeast extension. Well, anyway, through other things, it turns out the government found out that there was a company, Phelps Dodge, which is one of the world's largest copper companies, and they had a product that would meet the spec, but actually it exceeded the ductility. It had more ductility. That stress strain curve and energy went out even further. But for whatever reason, there was a spec, your ductility was supposed to be more than 10% and less than 20%. Why did it be less than 20%? Are you planning on stretching this like silver putty? No, okay? And anyway, we found out about this, and I said, hey, use the Phelps Dodge material. That spec is a silly spec, okay? It's like some of the Boeing specs, right? It's a silly spec, okay, I don't know why it's there. And they ended up using it, and they built it with the stuff. But the first British company had not obeyed Amtrak, and they actually put some of the stuff up down here near Providence. And they had a train run by, and it was the 4th of July. Arcs all along here. I mean, the wire was wavy, and the slider would bounce as it went along, and you get electric arcs, and the wire would have worn out in 3 months with that type of use. So it turns out I was right in rejecting the other product. But the reason they wanted to get that other product is they could buy that product for $2.5 million from Rome, New York. Or they could get it from Phelps Dodge for $7 million. And they were on a fixed cost project. So guess which one they chose? And what did they tell the federal government? There is no one else. And then when the federal government found out about Phelps Dodge, they said, well, why did you use Phelps Dodge? They didn't meet the spec. Well, wait a second, you were asking to avoid the spec, okay, over here in Rome, but you didn't even ask us or even tell us. In fact, you certified to us that there was no other supplier. So we went to a 5-day or 3-day mediation down in Connecticut. And there's stories about that too. But anyway, we ended up prevailing. But the next day, after the arbiters or mediators, wherever they were, came up with their decision, I was no longer involved. But the story was that the FBI came in and they confiscated all the computers and the passports of the senior management of the British company for fraud against the federal government. They had lied to the federal government. And I tell you, the Justice Department doesn't like that, particularly when you're trying to make a few $1 million off your lie. Okay, so that's another example of what happens and why. Okay, and I don't know what actually finally happened, but I'm sure there was an accommodation, and it probably cost the company quite a few $1 million for their fraud. Okay, I doubt that anyone went to jail. Okay, but nonetheless, you learn, don't cheat the federal government. Although I can tell you stories about Army brake shoes for Humvees. If you can get around using a government Justice Department attorney, do it. Don't use the Justice Department. Anyway, okay. So I keep on talking about hydrogen embrittlement. I decided maybe I can get this to work. I thought,
Well, it's just on there.
oh, okay, that was off. What's it doing now? Reboot. Okay, great. Anyway, I'm going to show a video that goes for about 10 minutes on hydrogen embrittlement of wells, okay, because it's actually just as good or better than anything that I could do, except I got to find it again. Oh, that's what's going on. Microsoft has decided it wants to do an auto update right now, rather than me use my computer. Okay, let's see. Safari has got this one. Right, Safari. Yes, there it is. And it's blank. Okay, well, let's go back to the beginning. Sound?
Pipe replacement and lost revenue.
Okay.
So
I had it all set up. Okay.
hydrogen cracking in pipelines can lead to leaks, ruptures, pipe replacement, and lost revenue. So what causes hydrogen cracking, and how can it be avoided? Unlike workmanship defects, such as slag inclusions, porosity, and undercut, hydrogen cracking is independent of the welder's skill. Instead, it depends on the materials, welding process, procedure, and the environmental conditions. Hydrogen cracking, also called hydrogen-induced cracking, hydrogen-assisted cracking, cold cracking, delayed cracking, and underbead cracking, typically occurs at stress concentrations, such as the root or toe of the weld, and can propagate through the weld metal or heat-affected zone. Hydrogen cracking results when three independent conditions occur simultaneously. Hydrogen in the weld, a crack-susceptible microstructure, tensile stresses acting on the weld. If one or more of the conditions are removed or reduced below a threshold value, hydrogen cracking will not occur. Because the susceptibility to hydrogen cracking increases with increased hydrogen content, this demonstration video will focus on limiting hydrogen in the weld. Welding processes such as shielded metal arc welding with AWS 18 type electrodes, gas metal arc welding, and gas tungsten arc welding are considered low hydrogen welding processes. The hydrogen content of a weld is measured in milliliters per 100 grams of deposited weld metal. A typical low hydrogen process produces welds with 4 milliliters of hydrogen per 100 grams or less. In contrast, shielded metal arc welding with AWS 10 type electrodes results in welds with hydrogen levels of 40 to 60 milliliters per 100 grams. That's 10 times more hydrogen. If a weld remains at high temperature after welding due to preheat, interpass temperature control, or post-heating, the hydrogen that was introduced into the weld has the ability to diffuse away. This is because the average diffusion rate of hydrogen in steel at 100 degrees Celsius or 212 degrees Fahrenheit is typically 1,000 times faster than at 20 degrees Celsius or room temperature. In addition to preheat, the wall thickness of the joint and number of weld passes has an effect on the diffusion of hydrogen from the weld. The following 3 animations, provided by DMT Fleet Technology Limited, show the hydrogen level for welds made on 1/4 inch and 5/8 inch thick pipe materials without preheat, as well as a weld on 5/8 inch thick pipe material with a 250 degree Fahrenheit preheat. The hydrogen levels are modeled after a typical cellulosic-coated AWS 10 type electrode.
10 is a
The hydrogen
cellulose
is
paper.
introduced during each weld pass and diffuses into the heat affected zone, base material, and surrounding atmosphere as the weld cools. The maximum hydrogen levels present 3 days after welding are 1.75 milliliters per 100 grams for the 1/4 inch thick pipe and 10.5 milliliters per 100 grams for the 5/8 inch thick pipe. The 250 degree preheat for the thick wall pipe allowed more hydrogen to diffuse away and lowered the maximum remaining hydrogen level to 8.75 milliliters per 100 grams. Post-heating following the completion of welding can further reduce weld hydrogen levels. Hydrogen can come from sources other than the welding process itself. It can be introduced by organic materials or moisture that are either on the electrodes or on the materials being welded. Hydrocarbons and water can break down into atomic hydrogen in the intense heat of the welding arc, which is readily absorbed by the molten metal. This is because the liquid weld metal has a very high solubility for hydrogen. But as the weld solidifies as it cools to room temperature, the hydrogen becomes trapped or supersaturated in the solid steel. You may be wondering how hydrogen can be trapped in the weld metal if no bubbles or porosity are evident. Let's look to the periodic table. Iron, the main element in steel, has a relatively large atomic size compared to the small atomic size of hydrogen. If you imagine the iron atoms are basketballs and the hydrogen atoms are ping pong balls, it becomes apparent that hydrogen atoms can fit into the spaces between the iron atoms. The following shielded metal arc welding demonstration will show the differences between a cellulosic-coated high hydrogen AWS 10 type electrode and a basic coated low hydrogen 18 type electrode. The low hydrogen electrode used has the designation H4R, meaning the hydrogen content of the as-received electrode is 4 milliliters per 100 grams or less, and it is covered with a moisture-resistant coating. The importance of proper maintenance of low hydrogen electrodes and the benefit of preheat is also demonstrated. Bead-on plate welds are being deposited using the shielded metal arc welding, or stick welding process. Immediately after completion, the welds are placed into mineral oil, so the diffusion of hydrogen from the completed welds can be seen. The first sample was welded with a cellulosic-coated high hydrogen electrode and placed into room temperature mineral oil. A large number of hydrogen bubbles can be seen slowly diffusing from the weld. The second sample was welded with a low hydrogen electrode. Compared to the first sample, much less hydrogen diffusion is evident. This coincides with the fact that approximately 10 times less hydrogen will be introduced to a weld made with low hydrogen electrodes compared to traditional cellulosic-coated electrodes. The third sample was welded with a poorly maintained low hydrogen electrode that was allowed to absorb moisture. Despite the moisture-resistant coating, we can see a large number of hydrogen bubbles diffusing from the weld, similar to the amount seen in the high hydrogen electrode. Preheating, interpass temperature control, and post-heating can be beneficial in increasing the diffusion of hydrogen out of completed welds. The weld made with a high hydrogen electrode was allowed to sit at room temperature until the majority of the hydrogen diffusion possible was complete. When it is placed into mineral oil that is heated to 250 degrees Fahrenheit, the temperature that we showed allows hydrogen to diffuse 1,000 times faster than room temperature. We can see that diffusion begins again, and a rapid release of hydrogen occurs. Therefore, welds that are preheated and allowed to slow cool or post-heated will allow more hydrogen to diffuse, reducing susceptibility to hydrogen cracking. So remember, limiting hydrogen in the weld can reduce the hydrogen cracking susceptibility. We've demonstrated low hydrogen electrodes introduce a small amount of hydrogen into the weld. However, improperly maintained low hydrogen electrodes can introduce approximately the same amount of hydrogen into the weld as high hydrogen electrodes. Finally, if it is not feasible to significantly limit the amount of hydrogen that enters the weld, careful control of preheat, interpass temperature, or post-heat increases hydrogen diffusion and reduces cracking susceptibility.
Okay, better than I could have put it. Okay. All right. So let's look. Looks like most of the hydrogen's gone, right? Still a fair amount.
Sir, can you check your connection on the mic? It might be jostling loose.
Got turned off for some reason.
Now it's good.
Okay. It takes about a week or two for most of the hydrogen to diffuse out at room temperature. But if you heat it up to 250 degrees, it'll go a lot quicker. And in fact, that's what we do. If they're welding very high strength steels in the building bridges for the Federal Highway Administration, the welding code, AWS welding code, says you must wait, I think it's 72 hours before you do your non-destructive testing. Remember they called it delayed cracking? It turns out there are specs, ASTM specs, that say if you're heat treating like a helicopter rotor blade mast, okay, which is very high strength steel, can tolerate not 4 milliliters of hydrogen, but less than 1 milliliter of hydrogen. It's not welded, but this can be some of the steel, the hydrogen that's dissolved in the steel. One of you asked where the hydrogen comes from. There is usually, for a typical steel coming out of a steel mill, just because of the humidity in the air when they were melting the steel, you'll have 1 part per million, maybe 2 parts per million hydrogen in the steel when it comes from the steel mill. Not a problem if you're welding lower strength steels. When you weld, you can get that up to 30 parts per million, okay? And parts per million and milliliters per 100 grams is like a 1.1 conversion factor, so just think of them as the same. That 4 milliliter stick electrode, that's the best you can buy in normal commercial practice. okay? And we'll see a little bit later that gas metal arc welding, which is one of the things we're going to, has even lower hydrogen, and that's one of the reasons to go to it. But you can have, at very high strength steels like aircraft landing gear or helicopter rotor mast, when you're at 250 KSI, you can tolerate less than 1 part per million, okay? And that can be from the steel making process. Yes?
So can hydrogen cracking still occur in a weld like two years after the weld was completed?
No, not unless it's been reintroduced.
Okay.
Hydrogen, it will cure itself if you can get rid of it.
Okay.
I know of one case where it lasted a year, and that was in the high Sierras where it was frozen all winter. Okay, and I'll show you data showing that if you want to keep hydrogen in steel, in fact, I had a student do a thesis back 30 years ago on hydrogen cracking in armor steels. He was working for the Army over here in Watertown Arsenal. He would make his welds and within 5 seconds put them in liquid nitrogen so that he held the hydrogen in there so he could do his hydrogen analysis. But but see how fast it came out when I poured it in there? And to get the actual hydrogen you had in there at the time of the weld, you can only extrapolate back because you can't weld it and then have it in liquid nitrogen at the same time. Although Morris Cohen suggested that to me once when I was at Bethlehem Steel. Okay. That's where I learned about the impracticality of great academics. Anyway, yes.
I have a C-story about like the practical side of preheating. We were welding on a destroyer's rudder stool.
Yep.
And when you have to preheat thick steel, that heat goes somewhere and spreads. So you have, and if a welder has to get into a tight spot to weld, then they're basically welding in an oven, and they're burning. You could burn yourself just touching the surface that you're working on. So like the practical aspects of preheating can get pretty tricky.
In fact, in the Seawolf submarine, which was hydrogen cracking, because I actually determined it was hydrogen due to the lubricants on the gas metal arc welding wire. They had not cleaned the lubricants off well enough. Okay, that was my contribution. Lincoln Electric didn't like hearing that because they left the lubricants on. When they started to repair it, because they first had to dig all the welds out and then start re-welding it because Congress was not happy at the time. They don't like $2 billion problems. They actually started welding in what they call blue jelly suits. As you said, I mean, the foundations of a submarine are pretty heavy steel, and a lot of them are like egg crate construction, and you're crawling into some hole, and they had upped the preheats to 400 degrees Fahrenheit. How would you like to be the welder in a egg crate construction at 400 degrees? It is an oven. So they actually put them on little tractor, little wheeled carts like a mechanic uses underneath the car, right? And they put them in blue jelly suits, and they were pumping chilled liquid, blue jelly, through them, and they were breathing air through a mask, and they went in there, and they had like 10 minutes worth of welding time in there before they had to come out and someone else had to go in. Talk about pricey, okay? But at that point, they couldn't not repair this. It was like, sort of like the USS Cole, okay? They repaired the USS Cole at a cost that was greater than building a new destroyer, because they didn't want was it the Iranians? Who was it? Whoever bombed the Cole. They didn't want them to think that they had destroyed a capital ship of the U.S. Navy. So they spent more money to repair it than to build it. Okay. But that was sort of the Seawolf too. But they had blue jelly suits. You're right. It can be pretty miserable work. Okay. They don't use blue jelly suits anymore. We actually would use. Actually, the reason for that, they could get all the up to 2-inch thick plate they wanted from the steel mill fairly quickly, but they couldn't get the 4-inch plate for more than a year. Okay, for various reasons. It's just the capacity of the steel mills and things like that. So they had to reuse their really heavy steel plate, and that's what they were welding in the blue jelly suits. Okay, when they went to the other parts of the submarine, they actually just replaced the plate. It was cheaper just to scrap the old stuff. but then they had tighter chemistry control on the weld metal and on the base metal, so that they didn't get themselves to higher hardnesses and greater susceptibility, and to keep the hydrogen down. But these problems show up all the time, just like Don Sataway sent me an email in the Bay Bridge in California. It's coming from corrosion. They have these big, probably I think they're 4 or 6 inch diameter steel tie rods, and they started corroding, and the corrosion process creates some hydrogen that diffuses into the steel, not as much as welding will. And they said, oh, they would crack within a couple of weeks. Well, that's hydrogen. The hydrogen usually will diffuse out within a few days. For federal highway stuff, you don't do your inspection for cracks until 72 hours later, because the cracks usually form in the first few days. The U.S. Navy in subyard waits 7 days, okay, to make sure hydrogen cracks have time to form if they're going to form. What good does it do to inspect it if the cracks haven't formed yet, and they form after you inspect it?
Is the reason the tolerances for the high strength steel is a lot tighter for hydrogen because the high strength steel is more brittle based on maintaining carbon to be high strength?
Potentially more brittle. What it is, and they actually had, they had the Venn diagrams, the 3 circles? Did they have that in there? Okay, so they had the 3 circles. And this is the way the corrosion folks typically talk about stress corrosion cracking, hydrogen embrittlement, a number of corrosion processes. And frankly, hydrogen embrittlement can be considered a corrosion process. So, fight corrosion into everything about steel, right? But you have stress, you have to have 3 things. Stress, a microstructure that's susceptible, and in this case, we're talking about hydrogen embrittlement, you have to have hydrogen. No hydrogen, you don't have a high stress, you won't have hydrogen embrittlement. You don't have hard martensite. Martensite is the most susceptible of all the steel structures to hydrogen embrittlement, at all other levels of stress and hydrogen. And the reason they like to do a Venn diagram is the problem occurs at the intersection of all 3 when you have all 3. If you have less hydrogen, this becomes a smaller circle, and it doesn't intersect the other 2. If you have less residual stress, that's why we stress relieve, you don't intersect. If you don't have a martensitic steel, well, how do we get a non-martensitic steel? HY80, HY100 martensitic steels. We go to high strength low alloy steels. HSLA 80, HSLA 100. We didn't have that technology in the 1960s. We only had quenched and tempering. But the Japanese developed what they called accelerated cooled steels. Actually, they were first done in sheet metal by Jones and Laughlin Steel in the United States in the 1960s for the automotive guys. But then we didn't do much with it. The Japanese had a huge shipbuilding industry, and they wanted to be more productive to keep the Koreans from catching up with them in the 1980s. And so they started developing high-strength low-alloy steels. The reason the U.S. Office of Naval Research sent me to Japan in the mid-1980s is because the Japanese had the best technology in the world for making HSLA steels. We didn't even have a steel company that could make it. The U.S. Navy was considering investing $100 million into a steel mill under what they call a Title III program, where the government can come in and pay for the capital equipment to produce something that the military felt was necessary. They wanted me to go over there and learn about how the Japanese did their accelerated cooling to make higher strength steels with lower carbon, lower hardenability, and therefore better weldability. High hardenability is bad weldability, and we'll get into that at some point, if you guys want to. Or we could just go on to things like aluminum and titanium, nickel and stainless steels and things like that. The stainless steels are still steels. Yes?
So is the reason the high strength steels can tolerate less hydrogen is because they have more martensitic or martenitic stainless or martenitic steel?
Martensitic?
Martenitic.
The HSLAs.
Well, the HSLA, because you keep
You reduce this with the HSLA, you have less martensite.
you
You have no martensite.
You keep making the statement that high strength steels can't have any hydrogen or very little hydrogen. Why?
Well, high strength, because the high strength steels have more residual stress locked in,
Okay.
okay? Remember, who was talking back there in the back about pulling the pipes together, jacking the pipes together yesterday, and then when you cut them, they go sping, you know? And that's, they have locked-in stresses. The higher the strength of the steel, the higher this locked-in stress, the bigger this circle. The more martensite, HY80, the worse this circle. So you make this HSLA, that's better. You make this lower strength steel, or you stress relieve it to get rid of the residual stresses, or you lower the hydrogen. We actually do all three because we don't want to have that intersection in the center, okay? You can shrink each one of those circles in size if you're clever, okay? But it costs money to do it. Yep. Oh, here we go.
Yeah, so quick question, I think, so US Navy nuclear power, like they beat brittle fracture into us, you know, very early, and everyone's very familiar with brittle fracture.
Yeah.
And so I wanted to ask, just to make sure I'm not making like, kind of washing my terms together. Brittle fracture is like pre-existing flaw, and, you know, in a hypothetical scenario, if you just create a material with no pre-existing flaws, then you can prevent brittle fracture. In practice, that's impossible, but that's very different than what we're saying here. We're saying the very structure, the atomic structure of the metal being used permits hydrogen to seep into the structure itself.
Yeah,
And
you
so
don't need a notch.
There's no pre-existing flaw criterion for the existence of hydrogen cracking, right?
Well, you always have flaws in the steel.
Okay.
Microscopic, no, seriously, microscopic, smaller than a human hair flaws, the hydrogen will diffuse to those. In fact, there, if you go on YouTube, you can find probably some of the in the 1950s and 1960s at Rensselaer Polytechnic, they actually took a piece of steel that they had welded and polished, or they may have introduced the hydrogen not by welding, they may have done it by, you can electrochemically introduce hydrogen by a rapid corrosion process. They had a notch in it, just like my torn piece of paper, and they would put tension on it, and they would watch they put some glycerin on the top, and look at it in a microscope, and they could see the bubbles coming right out of the cracked tip. The cracked tip is larger in volume, because you're stressing it in tension, and the hydrogen wants to diffuse there. And as it concentrates at the crack tip, it allows the crack to progress. And you can see in the microscope a growing crack, okay, of hydrogen. And you can see the bubbles coming out right ahead of it, because the hydrogen wants to diffuse to that crack tip unless you can diffuse it out to the air faster. And it will start even at these little inclusions. And people have found that, well, the Naval Research Lab found in the early 1980s, they could weld HY80 with lasers and have better toughness and more resistance to hydrogen in the weld metal because the laser actually vaporized away the inclusions in the steel. And they ended up with a super clean steel from the welding process that didn't have these little imperfections.
So we don't do that because it's cost prohibitive, I'm assuming?
Well, yeah, it's sort of a scientific curiosity. It proves the point that if you're ultra clean, you can't make steel that clean on a tonnage basis. Maybe 100 years from now we'll have some way to do it, but today we make steel that's 30 times cleaner today than it was 50 years ago. That's why we don't have laminar tearing. That's why we don't have hot cracking. Not hot cracking, but reheat cracking, okay? When you put it in a stress relief furnace and things go to the grain boundaries. But we still can't make perfect materials. And a lot of things you hear about materials, the nanowires and nanotubes and graphene and all this stuff, all those things are based on some physicist calculating on a piece of paper what he thinks the properties of an absolutely atomically pure, perfect material are. Okay? The head of GE Aircraft Engines, Bob Sprague, from 30 years ago, was a very frank speaking person. And he's the one who said, whenever you first hear about the properties of a new material, write it down because those are the best properties the material will ever have. And Jim Williams, who replaced him, used to say his corollary is, whenever you first hear about the cost of a new material, write it down. That's the cheapest that material will ever be. Okay? Well, it turns out that, where was I going with some of this? Bob Sprague had another quote. He says, physicists think that structure controls properties. And that's the big thing for materials. Actually, he said it, I've seen the quote twice. I'll give it to you the second way. He says, material scientists, who are wannabe physicists, okay, think that structure controls properties. Metallurgists know that defects control properties, okay? How big is that little notch, okay? And even microscopic notches in some cases are what limit your properties. I passed around that little thing the other day that was electron beam welded where we were cladding nickel alloy on top of a piece of steel. And that produced some of the cleanest microstructures because we were electron beam refining every little weld pass there. Kind of pricey, but you can make very clean material.
So you're saying when we're, making steel in space and welding it with lasers, then we'll have like the next order of magnitude of higher quality steel.
If you want to take your submarines and build them up in space, that's fine. But remember, it costs $10,000 a pound to get material into space, okay?
Unless you're mining it to begin with, right?
Yeah,
That's the next level.
Okay, anyway, okay. We need a move steel. You guys got a
Asteroid
code.
passing by, I'm gonna build something.
Okay, and there should still be some more.
Your project all lined up. There's your project.
It's not completely flat. There's still some there.
Armageddon.
I'm still gonna last to this asphalt. Orbital mining operation.
You know, I have to be careful, because if any of you guys were actually in the Navy, with the Air Force, they would actually believe that, oh, let's start building our submarines in space. To them, that is a feasible idea.
And then just what? Throw it back down. I mean, getting stuff back down.
Oceans are big, there's a real ocean down there. Someone up there.
I have a feeling something might break.